So now we are going to practice using table 8.1, the solubility rules on page 330 of your book, and see if we can come up with some molecular equations and net ionic equations for a particular combination of aqueous solutions. Okay, so here we have lead nitrate and potassium sulfate, and I provide you with the formula and I indicate that it is soluble, but you must check that if I don't give you the phase labels, if I just give you the substances. In fact, I may be writing lead, and this would be lead 2 nitrate. Okay, and so it's, you are responsible to know what nitrate is, you are responsible to know what lead 2 is, and to be able to provide me with the formula, because this goes back to previous chapters, and as I said, it builds. But so what we know here is, and we can start different ways. You can first write the complete ionic equation by splitting everything into ions. And so lead nitrate will split into nitrate and lead ions. And it is important that you indicate the charge here, +2, and you can figure that out, right? Knowing that nitrate is -1, and so this is not lead 4, it's lead 2. And then understanding that that 2 produces 2 nitrate ions. Okay? And then potassium and sulfate. Those are all the ions that are in solution. And then you need to go to your solubility rules, and you can look at the different rules. Nitrates are always going to be soluble, that we know. So what about sulfates? Sulfates are also all soluble, except for strontium, barium, lead, and silver and calcium. And so there you go, we have lead, so it's going to precipitate out Pb Pb SO4. It's going to precipitate out, and that's in a 1-to-1 ratio because they're both have the same charge. So that's going to form a solid, and then we still have potassium ions and nitrate ions. So that would be the complete ionic equation. So now you can go up and finish the molecular equation by providing PbSO4 solid and putting the potassium and the nitrate together as KNO3 aqueous. So that would be the complete equation. So for sure we're going to be asking you about that. And we should also probably balance it because we have 2 nitrates and 2 potassiums. And so that puts a 2 there. And finally, the net ionic equation, which is also important. For that, we look at what's happening here, right? So we have nitrate, that's on both sides. We have potassium on both sides, so that drops out, which leaves us with lead and sulfate reacting to form lead sulfate solid. So that is the net ionic equation. And the better you know those rules, the less time you waste. Okay, so here we have lithium carbonate and silver acetate. All acetates are soluble. I know that all lithium compounds are soluble, but what about carbonate? So I go to the carbonate rule and I find that carbonates are insoluble except for lithium, sodium, potassium, and ammonium. Okay, so that means that lithium, that silver carbonate's going to be precipitating out. So I can go ahead and write that down. And you need to pay attention to the charges. This is +1 and this is -2. So it's going to be Ag2CO3 solid, right? And lithium acetate, CH3CO2, and that's 1-to-1, and that would be aqueous. And then you can also balance that. We have 2 lithiums, so we put 2 lithiums as a product, and so that also means we have 2 acetates, so we need a little 2 in front of that, and that fixes that little 2. So it's balanced. That's also important. It's less important, but you should always have complete work. So now that I have the molecular equation, if I just ask you for the net ionic, you may be able to go straight to the goods and focus on that precipitation of Ag2CO3 NO3 solid. That means that both lithium and acetate have to be spectator ions, right? And so this is going to be 2Ag plus and 1 carbonate, CO3 minus, forming silver carbonate as a precipitate. That's the net ionic equation. If I don't ask you for the complete ionic, you don't have to split all these into, okay, we have 2 lithium ions and a carbonate ions. You don't have to, but for some it helps, especially initially, to do that. So I'm not going to do that for this particular example. I'm going to move on to the third and last example, and then we are ready to move on to acids and bases. So here we have ammonium hydroxide, which actually happens to be a weak base. But we can just deal with it based on the ignoring the fact that this is a base, right? Just looking at, we have hydroxides, we have ammonium here, NH4, and we know these are all soluble, and then we also know that not all hydroxides are soluble. And so that's one of the rules. The hydroxides are insoluble except for lithium, sodium, potassium, ammonium. Okay, and so then we have copper ions, which is +2, and we have 2 nitrate ions. Okay, so it's going to be the copper hydroxide that precipitates out, right? Copper is not one of the exceptions. So it is CuOH2 that precipitates out. And then we get ammonium nitrate, NH4, NO3 aqueous. And I messed it up again, right? This is supposed to go up here. This splits into NH4 plus and nitrate ions, NO3 minus, and we have 2 of those. We haven't balanced that yet, so we're going to have to balance that. You got to put a 2 in front of it, but I know I can complete the reaction now because I have CuOH2 and, like I wrote down here, NH4 NO3 aqueous. That is important. That is the complete molecular equation. That tells us everything we need to know. And now if I wanted to balance that, I need 2 ammonia. I had 2 hydroxides. I need 2 ammonium hydroxides, which fixes our ammonium problem. And then we have 1 copper and 2 nitrates already. Okay, and so for the net ionic equation, you take out all of the spectator ions, which is the ammonium and the nitrate, and you're left with copper and hydroxide, and it precipitates CuOH solid, right? So we have 2 hydroxide ions. That's the net ionic equation. That's going to be probably what the questions are about. Okay, we can have some different reactions that are related, but that deal with acids and bases. And so we already talked about what acids and bases are. We used the Arrhenius definition. Anything that furnishes H plus is an acid, and anything that furnishes hydroxide is a base. Now this is a different, here it says accepts a proton in solution. It's a different definition, but it works as well, because if you have hydroxide, it will accept a proton, right? It's called a proton hydrogen plus ion because hydrogen only has a proton in the nucleus and an electron. And if that electron is removed, we have H plus or a proton, just a single proton which has a positive charge. And that's the net ionic equation for most acid-base reactions. You always get salt and a water, especially for the strong acids and bases. And here are 2 examples of a strong acid and a strong base. So you can just use the solubility rules, right? You can just say, okay, so hydroxides are insoluble except for sodium, lithium, ammonium, and so on. So this is and then hydrogen is not a metal, but it's H plus, and so it's also then going to transfer. You try to recognize the fact that we have H and OH here. So for the net ionic equation. Okay, a couple more examples here. Well, no examples. It's just showing you what happens, right? A strong acid is going to dissociate completely into H plus proton and chloride in this case. You know, the two counterions, just like an ionic soluble salt would. You have complete dissociation into cations and anions. And all of the soluble hydroxides will do the same. They will split into sodium ions into metal ions and then hydroxide ions. And it's the hydroxide that makes it a base, and it's the H plus, the proton, that makes it an acid. And they can react to form salt and water, or water, H plus and OH. Okay, so here's a list from your book that tells you which one are strong acids and bases. And so hydrochloric, and you would do well remembering this. Now there's a chapter in UChem 2 that emphasizes it, and most of you are moving on to Chem 2 this summer, so you would do well thinking about this now, memorizing it. Hydrochloric, hydrobromic, and hydroiodic are strong. Those are the halides, right? So HCl, HBr, and HI are strong, but HF, also a halide, that's the exception in that group. That's weak. All the other ones, chloride, bromide, iodide are strong acids. So hydrochloric, hydrobromic, and hydroiodic acid are strong. Nitric acid is always strong, and sulfuric acid is also strong. And then we have perchloric acid. And then everything else is weak. Acetic acid, which I addressed already, it has that carboxylic acid component that makes it a weak acid. So all organic acids that are similar to acetic acid are weak. And then again here, the soluble hydroxide, group 1 here, lithium, potassium, and hydroxide. And then actually turns out that calcium and barium, which the author has listed as strong, but they're somewhat soluble, so they're not quite strong bases. But they're listed here as strong, so for this chapter, I guess that's what we're dealing with. And then we have ammonia here, bases, weak bases. All right, and so what happens here is ammonia will react with water to form ammonium hydroxide. And ammonia is actually a gas. I have that written here as aqueous, which that's fine. But what happens when you bubble ammonium gas through water, it will act as a base, and it will rip one of the hydrogens off to produce hydroxide. So ammonia actually produces hydroxide through back channels, right? So ammonia doesn't have hydroxide itself, but it produces hydroxide when it reacts with water. Now let's look at that a little bit more closely. So what we have is we have a nitrogen. If you draw the Lewis structure for ammonia, you'll have a lone pair here. Okay? And what happens is it will actually take that lone pair, will actually rip that proton off. So what you get is ammonium, which now has a plus charge, and hydroxide ions. Okay, so this is what all nitrogens will do that have a lone pair. There's another definition of acids and bases, a more inclusive, or a broader definition, and that says that electron donors can be bases. So electron donors are Lewis bases. And that's what all nitrogen compounds with 3 groups are, right? So you can then transfer that to other compounds. You can have a nitrogen compound, for example, that has CH3 groups instead of hydrogens. As long as that nitrogen still has a lone pair of electrons, it can do the very same thing that ammonia did. And so all of those nitrogen-based bases, all of these are called amines. They will do that, okay? So that's going to rip that hydrogen off and form trimethyl ammonium. So these make ammonium salts, all right? And so So anything nitrogen with 3 organic groups, right? Anything with carbon is called an organic group. This can be a CH3 group or a CH2CH3 group, you name it. Just similarly to the organic acids, which were carboxylic acids, where you had a different group making it acidic. So nitrogen, if you see a nitrogen like caffeine, if you see that there are 3 nitrogens in caffeine that have lone pairs, and so caffeine is basic. Yeah. Okay, so let's look at weak acids. Like I said, it's the same idea. The one that's listed in the table is HF, and so every time you see the equilibrium here, that most likely implies that we have a weak acid. And so that H plus actually attaches to the H2O, right? So with the water here will take up that hydrogen, that H plus, and turn into a so-called hydronium ion, right? So you can either see it written as this with water included, or just without the water going to H plus and fluoride minus counter ion, spectator ion in this case. Well, not quite right. You'll look into this in more detail in chapter 14 and 15 for Chem 2, what happens to here, right? But every time you see this equilibrium error, okay, that means weak, right? And most of the time it's 95% sticks together, and very little of this H plus or hydronium ion is kicked out, right? Okay, so emphasizing structurally what makes an organic acid an acid. It is that C double bond O OH functional group called a carboxylic acid. This R group is irrelevant. It can be a methyl group, an ethyl group, it can be a propyl group, it can be a phenyl group. Those are all organic acids, organic groups, okay? This will weaken that bond, and some of it will be transferred to the oxygen to form this hydronium ion. Okay, let's take a look at a couple of these reactions involving acids and bases, and you need to be able to recognize that's what we have. So acids and bases usually react to form water and some sort of salt, okay? Salt is just any ionic compound. It doesn't have to be sodium chloride. It can be barium chloride or barium nitrate or potassium nitrate or sodium sulfate. Any of those ionic solids are in general called salts. Okay, so we have hydrochloric acid and sodium hydroxide. If you recognize the hydroxide, most likely we have an acid-base reaction. So the hydrogen and the hydroxide form water together, leaving NaCl, and that's exactly what's happening here. Again, hydrochloric acid, which is a strong acid, and barium hydroxide, which is, according to the table, a strong base. Also, again, no equilibrium here. Reacts to go to completion to form barium chloride, the salt, and water. And so we indicate here water as a liquid, as a product. Same thing is true for weak acids here. This is acetic acid. All right, so acetate and hydrogen together makes acetic acid. But we are adding it to a strong base, which means, and I'm going to go back, okay, so what that means for this particular reaction, if 95%, if only a little bit of this H plus is ripped off, what that base will do, it's going to keep ripping, it's going to keep reacting with this to form water and hydroxide, right? The hydroxide is going to keep forming water with the hydronium ion here. And so it shifts this equilibrium, it depletes the acetic acid. So you basically, let's put it this way, it's the hydroxide is going to keep on going after that. That may be a little bit easier to understand. There's a lot of hydroxide here because that is very soluble. All of it's going to go to hydroxide here, right? All of it's going to break into potassium hydroxide, which will then rip this off the acetic acid and shift everything completely to form potassium acetate. So there is no equilibrium here, but you just need to simply recognize we have a base and we have an acid, and it will form water and the salt. Now there are some other reactions that are important involving acids and bases. not all the time, but here in this case, right, if we have sulfites, hydrochloric acid is an acid here, right? So if you add that, if you have any kind of carbonate like shown, it's going to produce carbon dioxide. So that's a gas evolution reaction. So you need to watch out for carbonates and bicarbonates. Hydrogen carbonates will do the same thing. HCO3 compound, something like sodium bicarbonate. But that's not part of the periodic table, right? I mean the solubility rules, except we know this would be soluble since sodium compounds are all soluble. But for the most part, if you have carbonates, you are going to produce carbon dioxide. So it's not quite, this is basic, but not according to your table. So we have this H plus that's going to react with the carbonate to form carbon dioxide. That's something that you should probably remember, gas evolution. And you still get water like you would in a salt, whatever is left over, right? So calcium chloride's going to form. And so these other ones also produce gases here, like hydrogen sulfide will produce a hydrogen sulfide gas here. All right, okay, that's the gas. Any kind of sulfides, potassium sulfide, sodium sulfide, that is aqueous. The soluble sulfides here, group 1 and ammonium, will produce hydrogen sulfide gaseous. So it's not going to be a solid, it's going to be a gas. That's the only difference. And as I said, carbonates, which I've drawn down there, and sulfites, which are also not part of the solubility rules, but hydrogen, here's sulfurous acid here, not sulfuric. Sulfuric would be H2SO4. This is sulfurous acid, H2SO3. It produces sulfur dioxide as a gas. Again, you get a gas, water, so acid-base reaction, and a salt. And finally, we already looked at ammonium here. Ammonium hydroxide will produce ammonia gas here, right? So if you have ammonium chloride and potassium hydroxide, every time you have NH4 involved, right? There's a lot more chemistry to this, but I'm going to leave this for chapter 14. For now, focus on especially the carbonate, right? And hopefully maybe you'll even remember that H2S and SO4 can be generated from the sulfites, ITE, and sulfites, IDE. That's 22 minutes. I'm going to wrap things up. Let me finish acids here, a couple more slides, and then we take a break before we go to redox chemistry. Sometimes we can have, and I'll make this short, we can have acids that can donate more than one proton. Okay, but these are all weak, right? This is carbonic acid. There are 2 hydrogens that can come off, and they come off one at a time. And same with phosphoric acid, which is weak. There are 3 hydrogens that can come off, and they come off in 3 stages depending on how much base is present. And so we'll take a break, and when we come back, we're going to shift gears completely and look into oxidation reduction reactions.